Okay, so let's start with the SVM intuition, right? So let's look at these pictures and we want to decide what is the best hyperplane, right? So in this case, let's look at this case. We have two classes, right? The stars and the circles. And we can separate these two classes using this decision boundary or this hyperplane, right? Or this hyperplane or this hyperplane. So if I ask you what is the best hyperplane to separate these two classes, the answer is pretty obvious, right? It's B. Why? Because B is classifying all the data points correctly, right? It's classifying all the stars correctly and it's also classifying all the circles correctly. While for A, if we used A, right, as the hyperplane or the decision boundary, we have with the stars, right, or in the stars side, we have 3 circles. So these will be misclassified. And if we choose C, then these two will be misclassified, right? So the best one is B. Why? Because it's separating the two classes better, right? We have all the data points correctly classified here, and all the data points here are also correctly classified, right? Now let's look at the second case. So this is the first case, correct classification. We care about correct classification. Now let's look at the same data, right? It's the same data, but now we have three other hyperplanes, right? We have A, C, and B like this. So if I ask you what is the best hyperplane to separate the two classes, the answer is also very clear. It's C. Why? It's pretty intuitive. Because C is separating this from this, right? It's separating the stars from the circles. It's separating them better than A and better than B, right? This is called maximizing the margin, right? The 3 hyperplanes separate the two classes. But which of them is the best one? Here, we care about maximizing the distance between the nearest data point of either class, right? So this is the nearest data point of this class and this is the nearest data point of this class, right? So the distance from here to here is called the margin, right? So we want to maximize this distance. So C is the best one that is maximizing the margin. Now let's look at the third example, right? Here, before looking at the third example, as you can see, the distance from C to the star is much bigger than the distance from B to the star or the distance from A to the circle, right? So that's why we choose C as our hyperplane, right? Now let's look at the third example. Here for this case, we care about correct classification and we care also about maximizing the margin. Here we didn't really care about correct classification because the 3 hyperplanes are actually classifying the data points correctly, right? So that's why here we care about maximizing the margin only. Now let's look at A and B. So for A, we are classifying all the data points correctly, right? The star here and the stars here are classified correctly and the circles are also classified correctly. But for B, we are misclassifying this star, right? It will be classified as a circle, okay? So in this case, which one is better or which one is the better hyperplane? Is it A or B? If we are going to use SVM or support vector machine, and we will explain what is support vector machine, you will see that SVM by default gives more weight to correct classification than margin maximization, right? So A is classifying all the data points correctly, while B is maximizing the margin, right? The margin here between this decision boundary and the nearest data point is much bigger than the distance from A to the star or to the circle, right? So B is maximizing the margin or concerned more about maximizing the margin, while on the other hand, A is concerned about correct classification. So if we use SVM, by default, SVM will give more weight to correct classification than margin maximization. So that's why if we use SVM with the default hyperparameters, you will see that A is the one that will be chosen. Okay. Now let's look at case number 4, outliers. So let's say that we have the same data set, the same stars and the same circles, but now we have an additional star, and this star is here, right? So it's very, very obvious that this should be an outlier, right? It's a data point that was added incorrectly to the data, so we needed to clean it, but if we didn't really clean it in the pre-processing part, we have it for the training, right? So it's pretty clear that this is an outlier. Now, we said that SVM will give more weight to correct classification than margin maximization. However, this also means that margin maximization is important. We didn't really discuss before margin maximization. We didn't really discuss the idea of maximizing the margin. We didn't really discuss it for linear regression, logistic regression, KNN, decision trees, or random forest, right? We didn't really discuss this idea. We didn't really have anything in the algorithm that waits for this, right? We didn't really have something like this. While for the SVM, as we are going to see, maximizing the margin is important, right? So that's why if we have an outlier in our dataset, SVM will detect these outliers and ignore them, right? Because if we try to find a hyperplane that separates these two classes 100% correctly, this will be at the expense of maximizing the margin with a huge difference, right? So that's why SVM will choose to maximize the margin even though if we have incorrect classifications, right? So if we have any misclassifications, this is fine, but we care also about maximizing the margin. So that's why SVM can detect the outliers and ignore them. Now, let's look at case number 5, and this is one of the most important things to use for SVM. So if we have non-linear hyperplane, so if we look at this example here, we have circles, and outside of the circles, we have the stars, right? So if I ask you what is the best hyperplane here, you'll tell me, okay, we can have a circle, right, that can separate the circles from the stars, right? This is our hyperplane. Okay, now SVM solved this, right? And this is a problem for other algorithms, right? For the KNN, we cannot really do so using a linear separator, right? We cannot really do so using a linear separator. What I just said is that we are going to use a circle, right? And the circle is basically a non-linear hyperplane, right? So how we can draw a non-linear hyperplane using a linear separator? So SVM solved this problem by introducing a new feature, right? So we have here X and Y. So SVM will introduce a new feature called Z, and Z will be X square plus Y square. So if we take each point here, take the X value and the Y value, square the X, and then add the square of the Y, and now we have Z, right? So we now have X and Z instead of X and Y. So if you look at the data in the new plane, right, we transform the data from XY to XZ, right? As you can see, now the data is separated with no problem whatsoever, right? So we can have a linear separator just like this, and now the data is solved and we can separate the two classes in the new hyperplane, right? So this feature is not added manually. It's done using something called the kernel, okay? And the kernel is basically a function. So what is the SVM kernel, or what is the kernel in general? The kernel is something that is really very intuitive. It's just a function that takes low dimensional input data and transforms this low dimensional input space into a higher dimensional space, right? So we take these two features, right? They are in 2D, right? And we go to the 3D, right? So we have Z is X square plus Y square. So it takes low dimensional input space and transforms this low dimensional input space into a higher dimensional space. And by doing so, we can convert the non-separable problems, right, or not linearly separable problems, just like this, to a linearly separable problem, right? Using just a linear curve here, we can separate the data points, right? So it's mostly useful in non-linear separation problems. Okay, so SVM kernels, or the kernel idea, is mostly useful in situation like this, when we have some data points and we want to separate the two classes from each other, and we can see that there is a pattern to separate these two classes, but we cannot really do this pattern in linear space, right? We cannot really do a linear separator in this low dimensional input space. So we transform this low dimensional input data to a higher dimensional space, and we separate the data there in the higher dimensional input space, and then we just separate this data, and we now have a linear separator in the higher dimensional space. And we will see a visualization for all this, for this example specifically, and you will see how all this happens, so you have a better idea for how this algorithm works, right? But why maximizing the margin, right? Why do we want to maximize the margin? This is the topic for the next lesson. So let's go to the next lesson and see how we can maximize the margin and why we would even want to maximize the margin. So let's go to the next lesson.